as I already did in the last seminaries, in the last 2-3 seminaries, I'm always concerned with this problem about the SPN orbits in the real Grassmannians of dimension of a vector space of dimension 4n. This is a big problem. I mean, for me, it was a big problem because I started to study some. What I wanted to achieve is to determine the full set of invariants characterizing the SAP orbits of a generic subspace, any subspace, which I have in the 4n dimensional vector space under the action of this group, which I will recall you later what is this group, which is just an orthogonal group, but it's called quaternionic orthogonal group. It's part of the, is a subgroup of the orthogonal group of a generic subspace. The problem is that so far, even if I studied for a long time this problem, what I managed to do so far up to 2 months ago, let's say, I only managed to find the solution in some special cases that here I think I can show. Here, in the end of this slide, you see, I want to say that I started this talk a long time ago, this study a long time ago, but unfortunately, up to 2 months ago, I managed only to give some results about some special cases, exactly this one. I hope you see this in the at the bottom of the slide, the 2-dimensional subspaces. You see that? Do you see everything?
Yes.
Okay. The quaternionic, the complex, the totally complex, the totally real subspaces. Some subspaces that are defined as sigma complex, the summation of complex subspaces by different complex structures. And then the isoclinic subspaces. This just to show that 2 months ago, I had given the full sets of invariants only for these particular cases. These are important cases, but nevertheless, I wanted to solve the complete problem. Then I take any subspace U in a 4n dimensional vector space, and I want to know which are the invariants characterizing completely its orbit of any subspace. And this was quite complicated. Where do we start? I start just saying that what I managed to do in this last part, in this that I'm talking today, as you can see, the last case I studied and I spoke about last time we saw each other was this about isoclinic subspaces. Isoclinic subspaces is a very important case. I will define later, but I'll just give you now the whole idea of the things without going into details. These isoclinic subspaces, which are one of the cases I managed to solve, I realize now that they are more important than I thought, because through, let's say, by means of these isoclinic subspaces, I managed to find, hopefully, if there is no mistake, because I just finished this work, I find the solution to the whole problem. I mean, I could give the full sets of invariants of a generic subspace. And this is, I managed, because I had in my part already the study of isoclinic subspaces. And here now I realize that these isoclinic subspaces can be used and are the solution. I will give the solution to any generic subspace. Okay, this is the idea. So more or less, if I go to the beginning, this is the table of contents of, let's say, these slides. Many of them, I would say the most, are slides of the previous seminary. Because in that seminary, I spoke of isoclinic subspaces. So here, what is really new is this thing here, where I say, no, this one, the last point of preliminaries, which isoclinity with IU, JU, and KU implies isoclinicity. This is a new result, very important for what I'm doing today. And then another new result is just here, where in point 5, where there is the full sets of invariants of a generic subspaces, where I define this canonical orthogonal decomposition of a generic subspace U into isoclinic subspaces with the to reach the end of the story, which is the next point, the full sets of invariants characterizing the SPN orbits in the real Grassmannian. Okay, the rest, more or less, are things, also slides probably, because I took from previous conference, that you already have seen last time, but maybe now I'll try to refresh for those who were there, your mind, and give some new definition and theorems for people who were not there last time. Okay, so let's say, first of all, let's say what I'm doing. We say that in the frame of the theory of invariance for the action of groups on manifold, we study the SPN orbits in the real Grassmannian of the k-dimensional subspaces of a real 4n-dimensional vector space. This is what we do, as I said. Okay, the Lie group SPN, for those which is called the quaternionic unitary group, is the group of automorphisms of an Hermitian hypercomplex vector space that is a real vector space V, endowed with an Hermitian hypercomplex structure that is 3 anticommuting complex structure satisfying ij equal k, and then also jk equal I and ki equal j, cyclic permutation, and where this by this symbol we denote an Hermitian scalar product that is a definite positive definite scalar product with respect ijk are isometries or skew-symmetric, which is in this case would be the same because j squared equal -1. They're compatible complex structure, so the square to minus identity, and therefore skew-symmetric or isometry is the same. One is that SPN is a subgroup of U2n, which is a subgroup of S4n, which is a subgroup of O4n. An Hermitian hypercomplex vector space has dimension 4n and has the structure of an H model. We have an action of the H of the quaternions, the structure of H module. That is, we have an action of the quaternions on this space. So since V has dimension 4n, we can consider V endowed with an Hermitian quaternionic structure, which is the linear span of the hypercomplex structure, and denote by SQ the sphere of compatible complex structure of Q. That is, SQ is linear combination of ijk, let's say alpha I plus beta j plus gamma k, in order that a square, alpha square plus beta square plus gamma square equal 1. Then for any t in SPN, since t is the centralizer of, let's say, SP1, the representation of SP1 on the vector space, t commutes with A. TA equal AT. This is by definition. Now I jump the principal angle, I'll just go on. In our quaternionic vector space, we can define an Hermitian product also, and is just by using the Hermitian scalar product. And this is the expression x dot y is just a scalar product of x and y, then x and iy, x and jy, x and ky are the components of ijk of this quaternion. So the beginning of the story is that just this preliminary result, which I already spoke about, that we say that a pair of subspaces of a real dimensional M in the H module before n, U and W are in the same orbit, two subspaces of same dimension, if there exists some A in SPN such that there exists some A in SPN such that A applied to U goes to W, if there exists bases x1, xm, and yr1, ym of U and W with respect to which the Hermitian matrices are the same. That is, xi dot xj equal yi yj. Okay, but this is difficult. This is just theoretical because what do we do? What do we know? We don't know which are the bases. We should try in all the possible bases in U and W if it's possible to find some bases with respect to which the Hermitian matrices are the same, which is impossible, of course. So this is just the idea. But then we have to try to find a real solution to this problem. Then if we choose an admissible hypercomplex basis and we denote by U the set of triple standard bases, the standard basis I defined in the previous seminary. I mean, we have the omega I, omega J, and omega K standard form, the skew-symmetric, let's say, probably I have here. Okay, I have to recall what is the standard basis standard form. So if we have, let's take any A compatible complex structure, and we have a k-dimensional subspace. We denote by omega A for any two vectors the scalar product of x and IA y. Okay, this is a skew-symmetric form by the skew symmetry of A. And any skew-symmetric form, we know by linear algebra that it admits a standard form, and which is this one. And I just decided to find a standard form in which Aij I defined to be positive, or not negative. We call exact. What's up? Somebody speaking? What's up? Is everybody there?
Yes, we are here.
Yes.
There was somebody speaking or not? Did they hear?
No, I think by accident, some talk
Okay.
at home.
Okay, me
Have
too.
you
I
eaten
was...
breakfast or something like that?
Okay, okay. No, I thought somebody wanted to make some remarks or comments for it. Okay, then we call xi standard basis of a skew-symmetric form, in this case of omega A. And every two plane, xi plus 1 with I odd is a standard two plane. These standard bases are never unique. This is the point. But the standard subspaces associated to the same principal angle instead are unique. And we will work on this fact. Then we'll go back here. So we have, the theorem says that necessary and sufficient condition for a pair of subspaces U and W to belong to the same SPN orbits are stated in the theorem that let IJK be an admissible basis of the complex quaternionic structure. The subspaces U, M, and W, M of dimension M of V are in the same SPN orbit if and only if they share the same principal angles. That is theta I du equal theta I dw, theta j du equal theta j dw, and theta k dq equal theta k dw. For one and hence any admissible basis IJK, or equivalently, we could say that the singular value, if you remember in algebra, the singular value decomposition of some matrices, the singular value of the projectors, the U to IU and the U to JU to U to KU are the same as those from W to IW, from W to JW, from W to KW, three projectors for one and hence any admissible basis. This is the first point. So principal angles. Then the more complicated part is here. There exist three standard bases, which are always orthonormal, xi, epsilon I, and zi, here in U and in W, such that the relative position, that is the orthogonal matrices, the Gram matrices between these bases, is the same. This is Cij equals C prime ij, Cik equals C prime. So I have to find that in U and in W, there are two changes of basis, let's say two orthogonal matrices from the basis of standard basis of omega I to the standard basis of omega J, and the same from the standard basis of omega I to the standard basis of omega K, which are the same in U and in W. Again, it's a bit more simpler than before, but still is impossible to find still the solution in this case. So we say here, when dealing with the SPN orbits of a subspace U of a four-n-dimensional real vector space V, endowed with an Hermitian quaternionic structure, chosen an admissible basis HyperComplex IJK, it is natural to consider the vector theta I, theta j, and theta k of the principal length between the pairs U, IU, UJU, and QKU. But if the principal angles characterize completely the UN is the unitary group, so we speak this time of a complex vector space, and there is only one form omega I, completely characterize the UN orbit in the Grassmannian. In this case, the equality of the three vectors is only a necessary condition for a pair of subspaces U and W to share the same SPN orbit. As we said, in fact, it's just 0.1. In the complex case, 0.1 reduces to theta I equal theta U equal theta I W, finished. And there is not 0.2. So it's very easy, the complex case. I mean, even if it took some time to find out the solution, but anyway, it's much simpler. Here we have this problem of the basis. And so I say, the determination of the principal angles between a pair of subspaces, so principal angles, is a well-known problem solved by the singular value decomposition of the orthogonal projector of S onto T. Okay, so principal angle would be not a problem. But unfortunately, we have another part of the story. The problem to determine the SPN orbits in the Grassmannian of k-dimensional real subspaces for K turns then into the one of determining the existence of the triple of bases belonging to the standard basis of S and standard basis of T, satisfying the second condition. This is not an easy problem to solve because, as already said, for any A in the sphere of compatible complex structure, the standard bases of omega A are never unique. Anyway, I said in the previous work, I determined the full sets of invariant in these particular cases. So let's, since I will show the importance of the, I already stated, I think before to you, the importance of the isoclinic subspaces, let's first recall the definition, some properties, and then let's go to the end of the story. Definition of isoclinic subspace. A pair of non-oriented subspaces A and B of same dimension are said to be isoclinic, and the angle theta in 0 pi over 2 is said to be the angle of isoclinicity between them if either of the following conditions hold. One of the three are equivalent. The angle between any non-zero vector of one of the subspaces and the other subspaces is equal to phi. That is the angle between one vector and its projection on the other subspace. Then G composed with G transpose is a scalar matrix. It's cosine square times the identity. Cosine square phi times the identity. For the matrix G of the orthogonal projector, the Gram matrix, with respect to any orthonormal basis, AI small of A and J small of B. So I have these two subspaces. I took in any of them the matrix. I take the matrix of orthogonal projection with respect to this orthonormal basis, and then I make G transpose, and it comes for any basis, it will become a diagonal matrix, a scalar more. But more clearly, if all principal angles between A and B are equal to phi. All principal angles. So let's try to, okay, we denote by IC to M, IC in the sense of isoclinic to M, the set of 2M dimensional subspaces of B, such that for any A in SQ, the pair AU is isoclinic, any pair. When do we not need to specify the dimension? We just use the notation IC, and we call them isoclinic subspaces. The fact that we consider only even dimensional subspaces, because we said I to M, IC to M, follows from the proposition that let U be an odd dimension isoclinic subspaces, then U is a real Hermitian product subspace. Necessary. What is a real product subspace? That is, for one and then any admissible basis IJK, the pairs U, our subspace, and IU, which is another subspace, U and JU and U and KU are strictly orthogonal. That is, all principal angles between these pairs are 90 degrees. Then the set IC odd dimension is a set of all and only the real Hermitian product. Okay, all real Hermitian products share the same orbit. Okay, so odd dimensional isoclinic subspaces are real Hermitian subspaces, and they are all in the same orbit, if they have the same dimension, of course. This is just, that's why we consider only even dimension. So the result that I added in this work, in this in this talk, the main result, which gives then leads to the final result, is that the isoclinic subspaces play an important role towards the complete solution of our problem. This is due to the following theorem, whose proof we will give afterwards. Okay, let U a subspace in this quaternionic Hermitian vector space. IJK is a admissible basis, and let's consider one of the three complex structure, I or J or K. Whatever. A subspace U in view admits I, if I choose I, canonical orthogonal decomposition into isoclinic subspaces. It's very important. The word important is canonical, because what we look for something canonical. We have so many bases, we have so many possible decomposition, but we are looking for something canonical, so that I can assign to every subspace some canonical matrices. You remember the matrices Cij, 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 and Cik. They should be canonically defined. Of course, these matrices depend on the basis, but then if I find some canonical basis, then I can say that these matrices are this, this, and this, and two subspaces are in the same orbit if they have the same matrices. But we have to refer to one base, or at least to one sort of matrix, because sometimes different bases can give rise to same matrices. What interests us actually is the matrices. We can have more standard canonical bases as long as we have one canonical matrix. So when we will show this, that any subspace admits an I-canonical orthogonal decomposition into isoclinic subspaces, we can state the theorem that these matrices that we are looking for to associate to a subspace U, the matrices Cij and Cik, are orthogonal sum of the blocks, so diagonal blocks, relative to the isoclinic subspaces of the canonical decomposition of U. So these matrices we look for are just diagonal blocks, and every block is canonical. So it's finished, the story. From the main theorem in 20 regarding the isoclinic subspaces and from the form of the canonical matrices in case of 2, 4, and 8 dimension, we anticipate here the final result. We anticipate, of course, you will not understand the symbols, but just to give you an idea, the final result, which will be explained in the next slides. So the final result is the SPN orbit of a generic subspace is determined by the triple theta I, theta j, and theta k, which are the principal angles between U and IU, U and JU, U and KU. And by the set of these four numbers, Xi, Ki, and Eta, and big delta, of the different isoclinic addends of U associated to the canonical decomposition. So every isoclinic subspace, every subspace has a canonical decomposition. So we have this canonical defined subspaces, isoclinic, and we will see that all subspaces, their orbit is determined by this by this set. Theta 1, theta j, theta k, theta I, theta j, theta k, and by Xi, Ki, Eta. Okay, so then it's easy to write down the matrices by adding in a diagonal form, okay, in diagonal block form, these matrices relative to each addend, and the story is finished. We have the principal angles and we have the matrices. Alors, Okay, now we have shortly, because I don't have much time, in 5 minutes, I want to just to recall the main results about the isoclinic subspaces, since they are so important. When I spoke about this isoclinic subspace last time, I didn't know they were so important to me, to the problem, because I thought they were important just for determining the orbit of this isoclinic subspaces. Now I find out, step, I repeat for, sorry if I repeat many times, that this isoclinic subspace is also a good tool, an important tool, a fundamental tool to find the SBOM of any subspace, not only of themselves, of course. So the first result that it was difficult to prove last time, and in fact I didn't state it because I couldn't find a proof, but now I did, is this one, that if a subspace, 2n-dimensional, is isoclinic with IU, subspace U, is isoclinic with these other 3 subspaces, IU, JU, and KU, of course with different angles, are isoclinic, these 3. Then U is isoclinic. That is, U is isoclinic with any, not only with I, J, and K, U, but with any A belonging to the quaternionic structure. It seemed obvious, but it wasn't. I could manage to prove this only in dimension 4 and 2. Dimension 4 was the most I could manage to prove. That if U and IU, U has dimension 4, then IU has dimension 4. U and JU, U and KU are pairs of planes of 4 planes. Then suppose they are isoclinic. In dimension 4, I could manage them, then they are isoclinic with any A belonging to the complex, to the quaternionic structure, which means that they are isoclinic by definition. But in dimension more than 4, I couldn't manage. Now I did it. That's all. I put here a sort of demonstration, but I don't want you to annoy you with all these details. It's a demonstration of this stuff, and I was happy to find out something which was obvious to my brain, but it was not, I couldn't manage to prove it. And this is very important now. Because of this, I could go on with the study. So if U is isoclinic with IU, JU, and KU, then it's isoclinic with everybody. Okay, when we speak about isoclinic subspace, we just have to see if some of the principal angles are equal to 90 degrees, if theta I or theta J or theta K. According if 1 or 2 or 3 of them are equal to pi or 2, we have the, I call it I orthogonal, just orthogonal if it's at least 1, or 0-1 orthogonality. This is if it's whether not orthogonal or just 1 orthogonal. This is just necessary in the separate for determining bases and matrices in these special cases, which must be considered separately, because otherwise I have some division by 0, which I cannot apply. Then I have to study these cases separately. Anyway, this is just a detail of the story. So let's start with two-dimensional isoclinic, two-dimensional subspaces that I already gave the solution a long time ago. Anyway, the two-dimensional subspaces are the simplest example of an even dimension isoclinic subspaces, U, E, U. In fact, by the skew-symmetry of the A-Keller form, any two-dimensional subspace is isoclinic with IU for any A. So two-dimensional subspaces and two-dimensional isoclinic subspaces are exactly the same thing. That is, the Grassmannian of 2 planes in 4n is exactly the set of 2 isoclinic planes. And when I studied the orbit of this oriented 2 plane, I defined this, I did it a different way compared with what I use now. Now I said I look for these matrices. At that time, I was not looking for matrices, but I just introduced the imaginary measure, which is just the imaginary part of the Hermitian product of any 2 vectors. And this is an invariant of a 2-dimensional subspace. And SPN preserves this quaternion, imaginary quaternion. And also, and then in fact, I say that the theorem, the imaginary measures, with just these values, this imaginary quaternion, represents the full set, the full system of invariants for the SPN orbits in the real Grassmannian of two planes, as well as the Grassmannian of the oriented two planes. There is a plus here. That is, a pair of two planes U and W are in the same SP orbit if they have the same imaginary measures. This was, let's say, an old way of, I used to say something that now I would say in this way. I would say that in a two-plane, I consider a triple standard basis, x1, x2, x1, y2, x1, z2, centered on a common leading vector x1, because x1 is a principal vector, but the associated one is different, of the oriented two plane. Then by definition, we have the cosine theta I is this number, cosine theta j and cosine theta k are negative, and computing this xi, which is the scalar product of x2 and y2, k, x2 and z2, and eta, y2 and z2, where these three numbers can be whether plus or minus 1. One is that the matrices Cij with respect to the basis are given by these two matrices. It is straightforward to verify that this triple is an invariant. This is important, that if I change basis, the matrices remain the same. So I have many standard bases, but I have always the same matrices. This is exactly by definition. What is the definition? By definition, what is a standard is a canonical base and a canonical matrix. The matrices are always the same. The bases can be many, but they always give rise to the same matrix. Therefore, we call them, even if they're not unique, canonical bases. So remember, when we have two-dimensional subspaces, which are always isoclinic, we said, these are the two matrices. Okay, this is one is x1, x1, of course, then x1, y2, y2 is 0, y2, x1 is 0, y2, x2 is this number here I wrote before, is exactly the same. And they're all like this. I change basis, orthonormal basis, because it must be standard subspaces, and the matrices remain the same. Okay, finished for two-dimensional. Four-dimensional, this is new, because not all four-dimensional subspaces are isoclinic. But if U is isoclinic, then this is the angle. The first line, it gives you just the angle of isoclinicity with for any A. This is a trace of omega A, when omega A is the sum with the coefficients here, A equal alpha 1i, alpha 2j, alpha 3k plus, and then the omega A is just a sum with the same coefficients of the three forms. It's a skew-symmetric form, of course, sum of three skew-symmetric forms, and the trace, it gives you the divided by 4. You take the square root and then you divide by 4, and you find exactly the cosine of the angle of isoclinicity. Also here, we have this important thing. This is one of the first, one of the things that we will see afterwards, that is always the same. So if I take an x1 and I consider who is the x2, which define the standard two plane, x2 is given by this formula. If y2 is given by this formula, z2 is given by this formula. That is, I project x1, then I come back with minus I, or I minus 1, and then I divide it, I normalize. And these three vectors are they complete the standard two plane. That is, x1, x2, x1, y2, x1, z2 are exactly the two standard subspaces of omega I, omega j, omega k. So we consider these three numbers, xi, this product, chi, this proper eta, and they are the important result is this one. These three numbers, the proposition, forget about the claim. The proposition says that these three, chi, xi, and eta, are invariants of U. Okay, so whatever we change basis, I take another x1, and so I have another basis. I have another x2. Then the product, and then I have another y2, another z2. These numbers are always the same. Then I have to build the basis, the canonical basis of a four-dimensional vector space. Now I go fast, I just jump, and I will find a way to build them. I don't write it down now. Everybody can see these results in my previous paper. And in the end, I prove that these equalities, and I arrived at that I was looking for. These are actually 6 spaces. I need just 3, just x1, the first, the second, and the fourth, xi, yi, and zi. These 3 are what I call the chains, and then they will chain center on x1, on a common leading vector. Using this basis, we see that here these matrices, these 2 matrices, they are the canonical matrices, as I will say later, just next slides, of a 4-dimensional isoclinic vector space with respect to the basis that is written here, xi, yi, and zi, that are written here. What is gamma and delta? Okay. If you clearly, let's say from the beginning, this is important. Let's say that this subspace, the linear span of x3, x4, this 2 plane, and the linear span of x3, x4, x3 tilde, x4 tilde are the same. And these 2 bases are orthogonal bases, but rotated one with respect to the other. Then see here, it's an orthogonal matrix, and we call these values gamma and minus delta, this 2, or delta, this one. So you see the determinant is gamma square plus delta square, which must be 1. It's an orthogonal matrices. And in this case, we have that gamma is given by, which is x3 scalar tilde x3 is given here by this formula here, which uses only eta, xi, and chi. So it's just a function of these 3 numbers. Okay, then can be 1 minus square, the square root. So we have a doubt just about the sign. Can be plus or minus square root of 1 minus gamma square. Unfortunately, it's not unique, but there are 2 possibilities, plus and minus. Allora, so here it's written, the pair gamma and delta, I have 10 minutes, is an invariant of U. Okay. Then the proposition, the matrices Cj and Cik given in 8 with respect to the chains xi, ypsilon yi, xi, zy, centered on a common leading vector are invariants of U. So these 2 matrices are invariant. Okay. And we call them the basis and the matrices canonical bases and canonical matrices. So every time I say a canonical matrix of the 4-dimensional subspaces are these 2 matrices. For every base I choose, but a basis built in a way I did, that is a chain. I call them the chains. I can always find chains. I change chain, but the matrices remain the same. So every chain, xi, ypsilon, and zi are canonical bases. And these matrices are canonical matrices. There is only one. So here I state the proposition, the theorem, the invariant xi, chi, eta, and this big delta, together with the principal angles, determine the orbit of any 4-dimensional isoclinic subspace. In particular, if U is orthogonal or 2-dimensional or 2 planes decomposable, I didn't explain very well, in which case the first set reduces to the pair xi, chi. Okay, this is a particular case. Examples here, there are 2 examples that are in the article that I already published. For instance, I-complex subspaces, you know, a subspace is called complex, I-complex, or any complex with respect to any complex structure, let's say A-complex, A, if U equal AU, so the transposed by the transformated by A is the same as U. A and AU is the same, or I or U and IU is the same, then it's I complex. In this case, we proved that, of course, Ju and Ku are exactly the same thing. And so the angles, the principal angles, are exactly given by 1, by U and IU, which are the same. So the principal angle is 1. And then I called. That is the principal angle with respect to any complex structure orthogonal to I. Let's say with respect to J, with respect to K, and with respect to any linear combination of J and K. And this subspace HyperP is important because we show that here at the end, all 4-dimensional quaternionic subspaces, which are a particular case of a complex, quaternionic subspace is complex by any complex structure. So it's not I complex, J complex, it's complex by any A. But, and also an I complex subspace, the orbit is determined by HyperP, take theta HyperP. Here there is a mistake, there is not perp in this. See, no, it's okay, theta J, theta K, yes. Determines the SPN orbit of an I complex subspace where IJK is an adaptive base. Okay, so for complex subspaces and also quaternionic, when you know the value of this HyperP angle, that is the angle between U, the complex subspace U, and JU or KU, which are the same, when you know this angle, all subspaces with this angle are in the same orbit, as long as they're complex, of course. Then there are also totally complex, which means that IU equal U, KU and KU are orthogonal to U. In this case, also, we have a simpler case, all 4-dimensional totally complex subspace share the same SPN orbits. Okay. And also the real Hermitian product, which I said IU, JU, and KU are all equal to 0. The cosine are all equal to 0. And so all 4-dimensional real Hermitian products share the same SPN orbits. Okay, let's go fast because I have other 5 minutes at most. And so we jump just directly to the end. So after having studied the 2- and 4-dimensional isoclinic subspaces in the following, we consider the dimension more than 4. So we prove that similar to the result achieved in dimension 4, to any subspace of dimension more than 4, but even, we can associate 2 sets of invariants. Again, a triple K, C, and eta, and the pair gamma and delta, which determine the canonical form of the matrices. So gamma is a function, as it was before, of K, C, K, and eta. According to the previous theorem, the vector K, C, eta, and delta, and the triple, theta I, theta J, theta K, of the angles of isoclinicity with respect to a fixed admissible basis determine the SP orbit. This is what we prove. To prove this is quite complicated. It's a long 3-4 pages of demonstration, so I don't want to do it. But in fact, I better skip to the end of the story. I just give this theorem. Wait. So if I will say that any subspace clinic of dimension greater than 8, in each of these subspace, for every x1 I choose inside, there is an 8-dimensional subspace U8 containing x1, such that the pair U8 AU8 has angle theta A, which is isoclinic. For a chosen x1, the subspace is unique. So let's direct the matrices. I don't show now how to build the basis because it's just boring. And the 2 matrices in the end will be this one, the 2 matrices I'm looking for. These are the matrices of isoclinic subspaces of dimension 8. So of dimension 2, we already know. Dimension 4, we already know. Dimension 8, we already know. But every subspace, and so we go straight to the main theorem of isoclinic subspaces. That is the one that say, I read it. It's the important theorem about isoclinicity. So let you subspace of dimension 2m and fix an IJK and denote by theta I, theta J, theta K, the angles of isoclinicity. For K greater or equal than 0, if 2m dimension is 8k plus 2 or 8k plus 6. This is 2 modulo 8, let's say, or 6 the modulo 8. And U is decomposable into two planes. It's orthogonal sum of two planes with the same angle of isoclinicity of U. In this case, gamma delta are equal to 1, 0, and the pair C key determine the matrices. The SPN orbit, in this case, is determined by the angle theta I, theta j, theta k, and by this pair. More generally, okay, let's say, when the dimension is AK plus 4, then U is orthogonal sum of U of dimension 4 isoclinic, with same angle of isoclinity of U, and characterized by the same pair key gamma and delta. In this case, anyway, gamma square plus delta square equal 1, and the canonical matrices are determined by these 4 numbers. In particular, this case, of course, okay, is orthogonal. Okay. The SPN orbit is then characterized by theta 1, theta j, theta k, and by these 4 numbers. So we have 7 numbers to determine the orbit. 3 are the angles, and then these also are angles anyway. If 2m has dimension 8k, so 8, 16, whatever, then U is orthogonal sum of some 8-dimensional subspaces with same angle of isoclinicity of U. The canonical matrices are determined by these 4 numbers and okay, and the orbit by these 3 numbers and these other 4 numbers. Then if gamma square plus delta square equal 1, we are in the previous case. And furthermore, if C equal plus minus 1 and K equal plus minus 1, we are in the first case. Okay, so we are in the last 2 minutes and I finish, promise. So let's say this was old stuff. So I repeat now the new result. So let U be a subspace, any subspace. Now we finished speaking about isoclinic subspaces and IJK and admissible basis, and let's consider one complex structure, say for instance I. And then I state that a subspace U admits an I-canonical orthogonal decomposition into its isoclinic subspaces. So this is important. This is the proof that I put it here because it's a new result. From this theorem, we say that then the matrices Cij and Cik are orthogonal sum of the blocks that we already know relative to the isoclinic subspaces, which can be 2-dimensional, 4-dimensional, or 8-dimensional, no more. Then recalling the theorem about isoclinic subspace, we conclude stating that the SPN orbit of a generic subspace is determined by the triple theta I, theta j, theta k, and the set of these 4 numbers, which are invariants, of the different isoclinic addends of U associated to the canonical orthogonal decomposition. End of the story, I think. Yes. Okay, so the orbit is determined by 3 angles between x2, y2, x2, zeta2, and y2. Let's say y2, I say in Greek, y2, zeta2, and by this delta. Apart from the 3 principal angles, of course, which we said is a necessary condition to be satisfied. And if we are in a complex situation, these are also sufficient, but not in a quaternionic subspace. I hope I finished.